Good afternoon. We start now with the afternoon session. Maybe define it slightly better. Okay, so we start with the afternoon session that starts with the young talk list. We'll have some PhD students and postdoc, and they'll introduce their early work on fractional differential equation related topics. And we start with the first one, that is Angelo Casulli from Scuola Normale Superiore. So Angelo, start.
Okay, welcome everyone. Today I'm going to talk about fractional exponential sum. That is our work I'm developing with Leonardo Robol from the University of Pisa.
And questo acceso c'è un pulsantino di lato.
Okay, funziona by now.
Okay.
The numerical resolution of fractional PDEs is often needed to compute the inverse of the alpha power of Kronecker sum that is a matrix that has this form, where this symbol is the Kronecker product and A and B are two matrices. Now, our idea is to compute this matrix function by approximating the inverse of the function c to the minus alpha with a sum of exponentials, and then we can easily compute this matrix function by exploiting the fact that the exponential of a Kronecker sum is equal to the Kronecker product of the exponentials of the two matrices B and A. Our idea is to represent the function c to the minus alpha by its integral form, and then to approximate this integral by a quadrature rule to write the function xi to the minus alpha as the sum of exponential. We to approximate the integral, we use the sim quadrature rule. So first of all, we need to transform this integral into an integral defined on the whole real axis. The sim quadrature rule is essentially an infinite trapezoidal rule. So if we want to approximate an integral with this rule, we have to divide the real axis in smaller intervals of width h, and then we approximate the integral by the sum of the areas of the trapezoid. First of all, since we need a finite sum and we have to truncate this series, we want a function that decays fast at plus and minus infinity. And moreover, the error that we produce by the infinite trapezoidal rule can be bounded by the norm of f times this exponential, where the norm of f is defined as the integral of the modulus of f on the boundary of the strip of width 2 times d in the complex plane. The first substitution we used in the integral is this substitution here. And with this substitution, first of all, we have an integral that is defined on the whole real axis. And moreover, we have that the integrand decays exponentially at plus and minus infinity. And we proved that in this case, the error producing during the approximation can be bounded by c times the exponential of about n at 1 over alpha plus 1 for a small constant c. Actually, after this, we try to use another substitution that is the same as before, but we substituted tau with the hyperbolic sin of x. And with this substitution, the principal advantage is that we have an integrand that decays doubly exponential. And so we conjecture that the error in this case can be bounded by c times the exponential of n over the logarithm of n for a small constant c. Actually, we are still working for a theoretical proof of this second substitution, but the numerical experiment confirms that this method is better than the first one. Thank you for your attention.
So since we are going to run through all the speakers, we leave the question at the coffee break. So take note of who is and catch them down during the break. So we can go to the next one, that is Fabrizio Cinque from University of Rome La Sapienza.
Is working.
And I think for now it works.
Come si può?
Okay. Back and
Puntare.
Okay. Fabrizio, please start.
Good evening, everybody. I'm Fabrizio Cinque, a first-year PhD student at the Department of Statistical Science in Sapienza University. And my research so far focused on the state-dependent fractional Poisson type process. I would like to begin by showing you a new form of a Mittag-Leffler function, let me say a multivariate analog, an n-dimensional multivariate analog of the generalized Mittag-Leffler function, introduced by Saxena and other researchers in 2011. As you see, we have somehow the core of the Mittag-Leffler function, but we have a product of n factors here. And all the components of this summation, so the fact that we are considering an n-dimensional function, all the indexes of the summation are related here in this gamma function. Of course, how to give a probabilistic meaning of this multivariate analog of the generalized Mittag-Leffler function? That's the first question. A first answer is, well, we can actually compute the convolution of generalized Mittag-Leffler densities with several parameters. So we have independent generalized Mittag-Leffler distribution with index parameter ni, alpha I is the shape, and lambda I is the rate. Now, the convolution of this the densities results in Formula 1, where you can find the usual structure of the generalized Mittag-Leffler random variables, of the density of the generalized Mittag-Leffler random variables, except for the fact that, of course, we are multiplying n factors, since we have a convolution of n generalized Mittag-Leffler random variables. The core function, which was the generalized Mittag-Leffler function in the case of the homogeneous random variable, is now replaced by means of this multivariate analog, where the parameters of the rates and the index appears in, let me say, the usual way. Now, we can move to the state-dependent fractional Poisson type process. A very simple, an example I want to give you is the case where we consider a point process whose waiting times are independent random variables distributed like Mittag-Leffler random variables with which alternate n kind of couples of parameters, meaning that we have ni1 lambda 1, ni2 lambda 1 up to ni n lambda n. Well, the counting process having this kind of waiting times is of course a state-dependent fractional process with, let me say, index which is a vector ni and a rate n of an n-dimensional rate lambda, and the probability mass of this counting process satisfies the following differential equation, fractional differential equation. In fact, the D operator you see here is the Caputo, the Zervachin-Caputo fractional derivative operator. And as you see, these equations appearing in the first two rows, they are extremely similar to the usual differential system solved by means of the from the Poisson distribution and then the fractional the distribution of the fractional Poisson process, except for the fact that right now we have n different indexes of fractionality and then different rates which alternates one another. Of course, the initial conditions are always the usual ones. In the end, this is quite, let me say, maybe a little weird differential system. And I want to underline that we are working under the fact that ni1 is greater or equal than ni2. In a more general case, we have an integral differential system. And the solution of this system is the following equation, which represents the probability mass function of this counting process. Again, you can find the usual distribution of the Poisson, of the time fractional Poisson process, except for the fact that we have n factors and not only one. So lambda j times t to the power of ni j is appearing n times with each couple of parameters ni and lambda. And again, the generalized Mittag-Leffler function is replaced by means of the multivariate analog of the generalized Mittag-Leffler function. Thank you very much. This is
so we move to the next presentation that will be by Lorenzo Cristoforo, that I have not seen yet, ok? Prova a spegnere anche questa, solo questa davanti, grazie. And ok, this is the start. Yeah, it's in the dark. Okay. Okay. It's okay. This one is forward, backward, and the laser. Okay. Thank you. Okay. Please, Lorenzo.
Good morning to everyone. My name is Lorenzo Cristoforo, and I am a PhD student for the Department of Statistics of Sapienza University of Rome. I am within the group of Probability and Stochastics of the Department of Statistics, and indeed my research interests are fractional stochastic processes, probability theory, and fractional derivatives. Indeed, a problem that I'm currently studying is the kind of diffusion of bounded domain. Specifically, I'm studying a kind of diffusion led by Hadamard fractional derivative of a function that it can be defined as the usual form of a derivative, fractional derivative, but we don't have a convolution kernel, but we have a kernel that decays in time with a logarithmic behavior, and we have a sort of average in time of the first derivative of our function f. And we can define our fractional Cauchy problem through this kind of Hadamard derivative and the Laplacian operator on the open set D, bounded open set D in time from 0 to capital T, and we can fix our boundary problems such that the boundary is a Killing type. We would like to study the solution of this problem from an analytic point of view, so expressing it through the special function of the Hadamard fractional derivatives, and so through their eigenfunction, and through the theory of the inverse of stable subordinator, leading this to a probabilistic representation through a Brownian motion subordinated by an inverse of a subordinator. So thank you for the attention, and this is the main bibliography.
We move to the next speaker, that is Paola Ferrari from the University of Insubria. The slides. If you want, you can remove the mask, and just forget to tell them. Try if it works. Okay. Now the floor is yours.
Good afternoon, and thanks to the organizers for giving me the possibility to speak about this idea that I have started to work on with Marco Donatelli and Maria Rosa Mazza, which is on the topic of a fractional order per anomaly diffusion for image denoising. So, what is image denoising? Well, we observe an image which has been corrupted by some noise. And of course, we want to find the original image, we want to reconstruct it. The point is that we only know the observed image, and so reconstructing it without knowing, of course, the actual expression of the noise is an imposed inverse problem. And usually we know only some statistics on the noise, which we can exploit. Indeed, the noise usually is observed to be of some specific kinds, like a Gaussian noise or a certain pattern noise. And over the years, many methods to solve this problem have been developed. We want to focus on the paranomalic approach, which consists in finding the denoised image as the solution of a time-dependent anisotropic diffusion equation at a certain time t. So we will consider this equation here, which is a diffusion equation with the diffusion coefficient, which is a function of the modulus of the difference with the paranomalic, the fractional gradient with order alpha, which we take between 0 and 1. The function g is a function which depends on a thresholding parameter c, which needs to be estimated in some way. And so what it is new in our idea is the discretization that we choose. So today I will give you a sketch of an explicit scheme, then only to present the objects. Then of course we will focus on semi-implicit schemes for which we want to study how to solve the related linear systems. So what do we have here? We have the objects nabla, let's say, which discretize the standard gradient, and we discretize it on an 8-point graph. And in each direction, we take the difference of these two objects. For instance, the first one is the north direction, of course, then divided by the special step size in the formula. So this is the gradient. Instead, what do we do to compute the function g of the fractional gradient? We use the Grove-Vallet formulas, left and right depends on the point that we are considering on the graph. And this is like for northeast, south, and west. And for the points in between, we use basically the Pythagorean theorem because we consider that they are in the middle. Of course, other choices could be made, and we will also try this. This is a first numerical experiment. We will have to improve a lot. The image is a noisy image. Then we consider standard diffusion, which doesn't work, image B. Our approach with alpha equal to 0.5, which is in between, and alpha equal to 1 is the standard paranomalic approach, which works well with denoising and edge detection. But for instance, I don't know if you can see it, the image looks quite blocky because it is known to have a staircase effect. For instance, you can look at the leaves on the right lower corner, which are really blocky. And thank you for your attention.
Thank you very much for the presentation. I think we can go to the next one, that is Giuseppe Giordano from University of Salerno. Yes. Okay, this is the screen. Try if it works. Okay, Giuseppe, the floor is yours.
Good afternoon, everyone. I am Giuseppe Giordano, a PhD student of the University of Salerno, and today I present a project entitled Continuous Extension of Numerical Methods for Stochastic Fractional Differential Equations. This is a joint work with Professor Diana Conte, Professor Beatrice Paternoster from the University of Salerno, and Professor Raffaele D'Ambroso from the University of L'Aquila. First of all, I would like to introduce the definition of stochastic fractional differential equation in its integral formulation, described by equation equation 1, and where f and g are the so-called drift and diffusion function of the equation, and w of t is an m-dimensional linear process. It is important to note that the solution of a stochastic fractional differential equation is a random variable for each t. If Vg is equal to 0, a deterministic fractional differential equation are obtained. And our project is based on two building blocks. The first one is the following. I have a continuous approximant in the deterministic case, so for stochastic fractional differential equation, based on the idea of the collocation methods. And these works described very well the procedure of the continuous approximant on the collocation methods. The second building block is the following.
I know how to get a continuous approximant in the case of stochastic differential equation. So a stochastic differential equation is obtained from equation 1 in the case of alpha equal to 1. And in order to get a continuous approximant, we make the following ansatz, the following hypothesis. In a sufficiently small interval of length h, the solution of the stochastic differential equation can be approximated by this function described by equation 3, where L1 and L2 are the classical Lagrangian fundamental polynomial. Capital U1 and capital U2 are the values of the function UN in the collocation point T and I, where C1 and C2 are the so-called collocation parameters between both with C1 lower than C2 and both between 0 and 1. And without making any details, the numerical scheme is described by equation 4, in which it requires the solution of a system of two nonlinear equations in the known variable capital U1 and capital U2. And for example, if we set C1 equal to 0 and C2 equal to 1, we can obtain a continuous extension of the Euler-Mariano method, which represents the simplest numerical method to solve stochastic differential equation. And at numerical point of view, we can note that for different value of the collocation parameters C1 and C2, we can obtain different methods to solve stochastic differential equation. And all these methods exhibit the same weak order of convergence of Euler-Mariano method, which is equal to 1. And our project is based on combining these two procedures described above in order to obtain continuous extension of numerical methods to solve stochastic fractional differential equation. And in fact, it is not the first time that the stochastic case is inferred by deterministic case, and clearly with some manipulation. And these are some references in which the some properties are transferred from the deterministic to stochastic case. And thanks for your attention.
Thank you very much, Giuseppe. We can go to the last one, that is Giovanni Pagano. Okay, as I was saying, Giovanni Pagano from the University of Salerno. So, please, Giovanni.
Yes, thank you. Good afternoon, everybody. I am Giovanni Pagano, PhD in my first year at the University of Salerno. And in this talk, I will present an ongoing project with my research group in Salerno, Professors Conte and Paternosse. The title of this talk is Equation-Dependent Numerical Methods for Fractional Differential Equation. Our talk is based on Tase operators. These operators can be used to improve the stability properties of an explicit numerical method we can use to solve the first problem, the classic ordinary differential equation. By using the Tase operator, we slightly modify the problem number 1, obtaining this ordinary differential equation. So we multiply this operator, that is a linear function, by function f. As I said, this operator can help us to improve the stability properties of the explicit method we can use for solve the problem number 1. But for a matter of consistency, we want the solution of problem number 1. Therefore, we have to use a task operator of order P if we want to preserve the order of convergence of our explicit method. Okay, these are the families of task operators discovered recently. The first depend on only one free parameter that must be fixed in order to meet both accuracy and stability, good stability properties. The second depends on two p-free parameters, so we have a great choice. But pay attention, because we have an explicit method. But as you can see, at each time step, we have to determine the inverse of a matrix that depends on the equation, on the equivalent of the equation. Therefore, the computational cost is higher than a simple explicit numerical methods. With these two families of operators, the authors found stable methods order 2, and nearly stable methods of order 3. Our research concerns in applying the same technique on parallel and explicit methods, because instead of Runge-Kutta methods, we can reach a greater order, and they have also better stability properties. They don't suffer from order reduction if applied to very steep problems. And employing these three families of operators, we have found a stable two stages peer methods, explicit and parallel, and also nearly stable three stages Runge-Kutta peer methods using these three families of operators, of task operators. Therefore, our project is in applying the same technique on fractional differential equation. For a matter of simplicity, we can consider the analogous of explicit Taylor for ordinary differential equation. So we, as a starting point, we can consider this problem. And in fact, if we consider the analysis of stability only in the case with lambda as a real parameter, we can see that the stability intervals of explicit Taylor for ordinary differential equation and Euler for fractional differential equation are very similar. And this is a more proof of that if we apply this operator on explicit Taylor, we gain A0 stability for alpha greater than 1/2. But it can be proved very easily that we can obtain a stability on the explicit method for ordinary differential equation with this operator. Therefore, the starting point is to apply a slightly modification of this operator also on this method, and the project is in constructing thus explicit methods for fractional differential equation that are stable. The same thing of the stability for ordinary differential equation, A alpha stability. These are some reference, and so thank you for your attention, and thank you to the organizers.
Thank you very much, Giovanni.
Thank you.
And incredibly, we are on time. I never thought it. So thank you to all the speakers of this talk. These have been perfect. And I think we can move. We can move to the next thing in our program, that is a standard talk by Roberto Garra from University of Rome Sapienza, and you can ask, and that will talk us about atomic fractional equation and ultra slow diffusion. So, Roberto, the floor is yours.
Okay, thank you. So, the topic of my talk is fractional differential equation involving INdAM type derivatives, but I introduce this problem in the in the framework.
Okay.
I will give the motivation and I will introduce the problem in the context in the framework of ultra-slow diffusion. So I will give a short motivation, and then I will give some preliminaries about this operator, and then I will discuss some recent results from the probabilistic result point of view and the analytic point of view about fractional differential equation involving Hadamard type differential derivatives. So, first of all, the motivation, ultra-slow diffusion process. As you know, time fractional diffusion equation, there is a wide literature that gives the connection between anomalous diffusion, continuous time random walks, and time fractional diffusion equation involving Caputo type derivatives. This is what is well known in physics, but also in applied mathematics model. But there is also what is known as ultra-slow diffusion, where the mean square displacement goes as a power of logarithmic. Okay, as anomalous diffusion is really a generic because there are many different stochastic process, fractional Brownian motion, continuous time random walks, and so many different anomalous diffusion. Here, when we speak about ultra-slow diffusion, this is the same. There are many different ultra-slow diffusion, not equivalent stochastic process, when the mean square displacement go like the power of logarithmic function. For example, C9 diffusion, where the power of logarithmic function goes like beta equal 4. Other model are continuous time random walk, where we have expanding media, and these are recent paper about continuous random walk in expanding media. Scaled Brownian motion, where we have space or time dependent diffusivity coefficients. And also in the literature, we have interesting model where we have the connection with continuous time random walks and distributed fractional derivatives. This is the motivation of our study. Now, the first step in our paper, this is I'm introducing a paper with Alessandro De Gregorio, just published recently. And we used a quite modification of the definition of fraction of the Hadamard fractional derivative that is given by equation 2. You can find that the Hadamard fractional integral is well known in the literature from Kilbas in all the monograph of fractional calculus. Hadamard fractional integral are integral differential operator, where the kernel is a logarithmic function, and in the differential operator is not the derivative, but is a differential operator with a variable coefficient. Okay, here we have so you can define a Caputo type or Riemann-Liouville type counterpart of the operator, as you know, for all the fractional operator. And this is a particular case of the so-called Caputo fractional derivative with respect to another function. It is a really generic definition that is useful, in my point of view, when you want to study fractional diffusion, including in the definition of the fractional operator is a time-dependent diffusivity. Okay, This is a way to include this and a time scaling, because as you know, as you can understand, this definition can be obtained from the Caputo derivative from a time scale of the change of time, deterministic change of time. But it can be useful for ultrasonic fusion. Okay. So then properties, trivial properties in some way, because these are related to the well-known properties of the Caputo type derivatives. So, but in this case, if we apply this operator to the power of a logarithmic function, we have the equation 3, and the eigenfunction is given by Mittag-Leffler in the logarithmic function. Okay, so we can say that in this case, the eigenfunction of the operator is a composition of the Mittag-Leffler function with the logarithmic function. Okay. More general, in the more general case of the fractional derivative with respect to another function, we can say that we have the composition of a Mittag-Leffler with the time-dependent diffusivity. Okay. Okay. Now the first problem is the more general case, the fractional abstract problem. So what is known? We applied the well-known theory of the semigroup. Okay, so definition of C0 semigroup for the representation of the solution of an abstract Cauchy problem. We call what is a C0 semigroup. We know that given a C0 semigroup, we have a generator defined by the limit 6. And then we have that the application of the operator T to the initial condition F give the unique solution to the abstract Cauchy problem 7. Okay, this is the well-known theory, okay, based on the semigroup for the Cauchy problem. What is if I want to apply this theory for the stochastic representation in the basic theory, in the fractional theory, in the Hadamard fractional theory? This is the problem. So obviously the first step is if stochastic. Stochastic, first of all, I recall, given a Lévy process X, I know that we can say that X admit a semigroup operator given by equation 10. Okay, for time reason I go fast. Okay, I don't recall that the characteristic function is given by equation 8. The most important reason fact is equation 10. For any Lévy process, we have equation 10. Any Lévy process admit a semigroup operator. That is this representation. Okay, so if I want a stochastic representation for the solution of an abstract Cauchy problem in the well-known theory, classic theory, I go back here to equation 7. If L is the generator of a Lévy process, the equation 10 is the stochastic solution of the unique solution of the Cauchy problem. If in the abstract problem, L is the generator of a Lévy problem. Okay, a Lévy process. Okay, finally, preliminary for the main result. I need last preliminary. I need to introduce the definition of the inverse of a stable subordinator. As you know, there is a fundamental connection between time fractional derivative and inverse of stable subordinator. Because if you have, for example, a time fractional diffusion equation, you know that the fundamental solution coincides with the density of the Brownian motion time changed with the inverse of the density, with the inverse of the stable subordinator. So we have this strong connection between the fractional equation and this kind of stochastic process. Okay, so given all these preliminaries, I can finally give the main result, the main statement. The unique strong solution of the fractional Cauchy problem involving Hadamard type derivative, where in this equation L is the generator of a Levy process. The operator, the time fraction operator, is in the sense of the Hadamard type that I introduced in the introduction, in the first. I introduced the unique solution can be represented by means of this integral, where P is the unique solution of the non-fractional problem. Okay, is the unique solution. Going back, because no. Vuoi usare da qui?
No, anche con me stessa. C'è un po' di ritardo verso il
Okay, sorry. Yeah. Okay. P was the solution of the of this Cauchy problem. Okay, of the classical non-fractional Cauchy problem were related to the case where L was the generator of the Levy process X. Okay. Okay. This is the main result, where the role played by the Hadamard fraction derivative is a time scaling, a logarithmic time scaling, because fractional stochastic solution of a fractional Cauchy problem is given by representation 13 where you have the density of the inverse of the stable subordinator, and you have another deterministic time scaling of the time where is logarithmic due to the Hadamard. Okay, so you have the scheme is the classical scheme of the stochastic time change and deterministic scaling due to the Hadamard. Okay, now I go fast. Some corollary. For example, the case for me equal 1/2. You have that you can represent for example, if X is the Brownian motion, the Brownian motion for me equal 1/2 in distribution can be represented as a iterated Brownian motion with the deterministic time scaling, the logarithmic time scaling, and iterated from emotion. Moreover, if you specialize the operator L, for example, with the fractional Laplacian, you have obviously a beta stable process computed in the inverse stable subordinator with the time scaling, deterministic time scaling. Okay, it's an implementation of the well-known theory with the deterministic time scaling related to ultra-slow problems. Finally, some analytic results for the specific case of the diffusion. Obviously, for the diffusion, you can find the fundamental solution by means of the right function. All that you can find in the linear case for the diffusion can be found by means of the time change, deterministic time change. You have a logarithmic time by means of the right function, and you have this fundamental solution. And you can find that for me equal 1, you have that the fundamental solution coincides with the fundamental solution of the heat-type equation, where the diffusivity is equal to 1 over 1 plus t, with the diffusivity dependent by the time. Okay, this is in some way a form of ultra-slow diffusion. Okay, finally, for me equal 2 over 3, you can find another interesting case because you have a linearized Korteweg-de Vries equation, because the fractional equation is scusa, mi sono un attimino fermato. Che devo dire? Mi sono un attimo fermato.
Sto dicendo che la soluzione è terminata in serie. Ok, no problem. That's an application. Yeah.
Sì, do un attimino bisogno di prendere. Va bene, allora, d'accordo. Va bene. Allora, vediamo un attimino. Quindi io, sì, avevo quasi concluso comunque in ogni caso. Dovevo dire, quindi, in effetti, per concludere, che dunque, sostanzialmente l'approccio che
parlare in inglese perché
the main object of our study was to apply the Adamard derivative to a deterministic free-scale time in our model with the for the analysis of with the object of to apply this kind of model also in other contexts. Okay, so we will say also Lorenzo. We will study also problems, some, for example, in bounded domain, and so okay.
The talk. I don't know if there is any question from the physical audience or the metaphysical Zoom audience. No,
l'audience trascendente.
Okay, nothing from them. So let's thank again Roberto. Speaker. You have to.
Yeah.
Lo sanno. I think we have 5 minutes
Dimostriamo che c'è
to,
la sala.
before going to the next one. I think they hear me. Yeah.
Se lo vuoi avvertire online,
Okay, so the. Oh, okay.
Vabbè, lei non parla.
No, io vado, no, ok, sì.
Ah, vai online? Mica
Sì, ero giustamente solo per la. No, ma io.
no, online, cioè non vai su YouTube.
stiamo disattivando YouTube, però lo diciamo prima così
Va bene, andiamo su, ok.
No problem.
Okay. Cosa devo fare?
Niente, lasciamo.
Leave it this way.
Cioè rimane su YouTube. Rimane, no, è una scelta.
Okay, maybe before introducing Alessandra, we just wait a couple of minutes in order people that want to join.
Sì, abbiamo
Accendiamo
Yeah.
un po' la luce, perché sennò l'orario.
Ci sono tipo il canale YouTube, cioè c'è la e la
Nessun problema,
Non c'è quello che fa il tecnico,
no pressure.
si tratta di accendere lo specchio.
Just that.
Ok, va bene. Come vuoi, dai, capire come funziona, almeno sì,
Sì, c'è un po' di ritardo.
perché si pianta quello
No, però
Mostriamo un po' questa sala, questo. Sei sempre tu in primo piano? Che almeno si sappia che c'è gente.
C'è gente lì.
Io mando tu WhatsApp.
c'è anche il coffee break adesso, magari. Okay, I think we can start again with the next speaker, that is Alessandra Giannelli from University of Messina. And she will talk us about exact and numerical solution of fractional reaction diffusion equation. So, Alessandra, the floor is yours.
The talk
deals with the exact numerical solution of fractional reaction diffusion equations defined in terms of Riemann-Liouville derivatives. This is a joint work with Maria Paola Speciale. We present a procedure recently proposed for solving a wide class of fractional differential equations. This procedure combines the least symmetry theory with the numerical methods with the aim to find the analytical and numerical solution of the fractional differential equations. This procedure consisted of two different steps. In the first one, by using the least symmetry theory, we can map the original fractional differential equation into a new fractional differential one. Then we solve it analytically if it's possible, but if it's not possible, we propose executable numerical methods. It depends on the kind of the fractional differential equation that we obtain by applying the symmetry, partial or ordinate one. Then, by applying our procedure for solving the fractional differential equation, we obtain a highly accurate numerical solution, and this shows us the efficiency and the reliability of the proposed procedure that can be used for solving a wide class of fractional differential one. Okay, here we show you some examples of mathematical models that we consider in our study. We start from equation number 1. This is an example of fractional reaction diffusion equations defined in terms of Riemann-Liouville derivatives. We have the alpha order derivative with respect to t and the beta plus 1 order respect to the space. Here we report the classical definition of the Riemann-Liouville derivatives. Now we have k, this is the representative diffusion coefficient, and in this case, f is the source term that in general we consider it as a nonlinear function of the field variable u. Here, okay, we have considered also the question number 2. This represents an example of a more general fractional differential equation. In particular, we have the differential diffusion reaction 1. We have the term, the diffusion term, the reaction term, but also the dimension 1, where k2 represents the velocity that in this case we consider it as a constant, and in general we can consider it as a function. Also, we study, we apply our procedure for solving systems of two-time fractional reaction diffusion equation given by number 3, and also at the bottom of the slide, we consider also the 10-fraction reaction diffusion equation in two-dimensional space. Now we show you, okay. Okay. In the papers that we published in these last years on the topic, all in collaboration with Maria Paola Speciale and Marianna Ruggeri. In this slide, I want to show you the papers published this year, where, in particular, in the first one and the last one, we obtained the results that we show you today in my talk. Okay, this is the outline of the talk. It can be divided into different parts. In the first one, we briefly show the least symmetry theory that we apply to reduce the original fractional differential equations into new fractional differential one. In particular, we present two different cases. We present to you the 10-fractional reaction equation in a one-dimensional space and in two-dimensional space. In the second part, we present a numerical approach when it's not possible analytically to solve the reduced new fractional differential equation. We propose executable numerical methods. It depends on the kind of the equation that we obtain. Okay. I start showing you, briefly showing you the theory that can be applied, the least symmetry that can be applied for the partial differential equation of integer order. And after I show how this theory can be generalized for the fractional differential one. Then we consider the classical equation number 5, partial differential one. We can define the one parameter group of infinitesimal transformation given by number 6. Note that C1, C2, and beta are the infinitesimal. These infinitesimal characterize the generator of the algebra number 7, and these infinitesimals are found requiring that the condition number 8 has to be satisfied. Then the transformation number 6 allows to map the original equation into new ordinary differential one. This is the theory for the partial differential equation of the integer order. Now I'll show you how this theory can be applied for solving the fractional differential equations. In particular, we consider two different cases. The first one, we consider an example of a time fractional reaction diffusion equation in one-dimensional space. In the second case, we consider the same equation defined in two-dimensional space. Okay. We consider the question number 11. We find the invariant conditions number 12, where we know the presence of the infinitesimal C4, C1, C2, and beta. But in this case, the main difference between the case of a partial differential equation of integer order stands in 13, where eta alpha t is defined by means of the capital P that involves the Riemann derivative. Moreover, C1, one of the infinitesimal, has to be satisfied the condition reported in the bottom of the slide. In this way, by solving the equation number 12, we can map the original equation, the equation number 11, into a fractionally ordinary differential equation. In fact, we obtain the infinitesimal C1, C2, and beta reported at the top of the slide. Note that A1 is a parameter. We have the presence of the arbitrary function key. A1 and key has to be satisfied the constraint number 14. As usual, we set A1 equal to 1. In this way, we obtain the transformation number 15. This transformation allows to map the original model into the fractional of the differential equations reported in the slide. Note that the presence of the function phi is an arbitrary function, and note that this function characterizes the function f. I remember you that the function f is the source term involved in the original model. Then, if we are able to analytically solve the fractional ordinary differential equation, we can obtain the solution, the analytical solution of the original model by applying the inverse transformation that we can compute by the number, by the inverse transformation by the 15. Now I'll show you another case. It's represents a more interesting case because the equation reported in this slide can be reduced into different ways. In the first one, by applying only one Lie transformation, we can map the equation under study into a fractional partial differential equation. In the second way, we use two Lie transformations in order to map the original equation into a fractionally ordinary differential one. I start showing you how to map the equation under study into a fractional partial differential equation. I don't report more details on the Lie symmetry theory, but only the transformation number 17 that allows to map the equation under study into a new fractional partial differential equation. In this case, we obtain an equation of kind ADR, the reaction diffusion reaction model. Note that in the equation, in the new reduced equation, we have the function phi1 and phi2 that characterize the source term of the equation number 18, but this characterizes also the source term of the original model. Now, if it's possible to analytically solve the equation number 19, we can obtain the solution of the original model by applying the inverse transformation to be computed by 17. But now, I'll show you the second reduction. Then we start from equation number 19, seen before. By applying another Lie transformation, we map the equation in ADR into a fraction of the differential equation given by number 21. Also, in this case, we have psi1, psi2 arbitrary function, not we obtain an equation involving only the variable independent capital T, where the only dependent variable is the capital W. Also, in this case, we can analytically solve the question number 21. We obtain, by means of two inverse transformation, the exact solution of the region. But if we are not able to find analytically the exact solution of the new reduced equation, we propose a numerical approach for solving them numerically solving them. For this reason, at first, we introduce the Caputo formulation. It's well known that the Caputo formulation has the advantage that the initial condition take the same form as the initial condition of the partial differential equation of integer order, and in this way we obtain the initial condition that assume a physical meaning in agreement with many natural phenomena. Then we can rewrite the new fractional differential equation in terms of the Caputo derivatives. Now, we start from fractional ordinary differential equation number 25 that we obtained before by applying two transformations. We report the classical definition of the Caputo fractional derivatives. It's linked with the Riemann-Wheel fractional one. And in this way, we can rewrite the equation number 25 in the form 26, where we have the Caputo derivative. Note that in this case, we consider vanishing initial condition in order to have the corresponding between the Riemann-Wheel derivative and the Caputo one. Now, in order to perform a comparison, in order to show the reliability and efficiency of our procedure, we show you an example of exact solutions of the fractional ordinary differential equation given by number 28. By means of the inverse transformation, we obtain the exact solution of the time fractional ADL model, and by means of another inverse transformation, we obtain the exact solution of the original model that reported in the bottom slide. In this way, we are solving an time fractional reaction diffusion equation in two-dimensional space. Here we report the complete form of the exact the analytical solution of the model where the source term is given by 32. And now I show you the compare. In order to solve the fractional ordinary differential equation, we propose a classical trapezoidal method. We propose it for its very good properties of accuracy and stability. This is an implicit method in conditionally stable one, and the method has an order of convergence equal to minimum between 1 plus alpha and 2. Here we show the comparison between the exact numerical solution obtained for different values of alpha. On the right, we have the tail of the solution, and we know that the numerical solution that we obtain by solving the fractional ordinary differential equation by trapezoidal method are in good agreement with the exact solution. In the bottom of the slide, I repost the parameters that we set for the computation. Now, the exact and numerical solution are used in order to obtain the exact numerical solution of the original models by applying to the inverse transformation. Here we show you in the top the numerical solution of the ADR model on the left and the solution of the original model in polar coordinates. In the bottom, we report a comparison between the exact and numerical solutions. And these computations are performed for alpha equals 0.5 at final time equal to 1. Now, in order to show the reliability and efficiency of the procedure, we show you in this table the maximum norm error and the order of convergence. As expected, we obtained an order equal to 2. I remember that is the same order of the trapezoidal method that we use for solving the fractional differential equation. The maximum norm error is between exact and numerical solution of the original model. Then we obtain the same order of the numerical method that we obtained. In the second case, we start from the time fractional ideal model. In this case, also in this case, we introduce the alpha order Caputo derivatives. It's linked with the Riemann-Liouville 1. And we can rewrite the equation in terms of the Caputo derivative as reported in the equation 35. Also, in this case, we consider vanishing initial condition, setting U, capital U equal to 0 for all z. In this case, we propose the classical formula L1 in order to approximate the Caputo derivative. And as usual, we consider the second order difference formula in order to approximate the first and the second derivative with respect to the space. And in this way, we obtain the classical L1 infinity difference method as reported in the first case. This method is implicit and conditionally stable, and note that the order of convergence in this case is equal to 2 minus alpha in time direction and equal to 2 in x direction. In order to perform a comparison between this model and with the numerical results obtained before, we consider the model as reported in this slide, and note that the parameters are set as before. In this way, but note that in this case we not are able to obtain the exact solution of the model understand. We report only the numerical solution as seen before. In the top, the solution of the ADR model, capital U, and on the right, the numerical solution of the original model in polar coordinates using x and y variables. Also, in this case, in order to show the reliability of our procedure, we show you the maximum norm error and the order of convergence, and as expected, we obtain the same order of the L1 numerical method. Okay. Now, okay, this is kind of summarized. We starting from two-dimensional time fraction reaction diffusion equation. In order to solve this equation, we perform two different ways. By applying the Lie symmetry that represents the first steps of the procedure, we map the original equation into time fraction ADR model, and we solve it by the L1 numerical method. In second way, but in second case, we obtain the fractional of the differential equation by applying to the transformation. By applying our procedure, in both cases, we obtain a high accurate numerical solution. Remember that the order of accuracy depends on the kind of numerical method that we use. And not that from numerical point of view, the L1 method has a higher computational effort with respect to the numerical method that we use for solving the fractional or the differential one. In fact, for the computation that we used before, we spent 2.3 seconds by L1 scheme. In the second case, we spent 0.002 seconds for the trapezoidal method. From numerical point of view, it's obvious that for applying L1, we need only one transformation. In the second case, we need two transformations. But if we have to make more computations, changing the parameters, it's obviously more convenient to use the trapezoidal method, because the transformation, we compute the transformation only once, and then we can compute perform a lot of experiments only changing the parameters, and the solution can be obtained by inverse transformation. And last slide, we show you the future work. We are working about, we are studying a mathematical model governed by a system of two time fraction reaction diffusion equations. Not possible to consider a system of more time fraction reaction diffusion equation describe the RNA interaction. This is the paper in the preparation of the topic, considering another mathematical model. I conclude.
Thank you very much for the nice presentation. I if there is any question from the audience or from I have one of I have one of my own. So you have to compute this transformation for each time step.
Only at the beginning of the performing transformation, and then we solve only the
transform problem.
And after
you transform it back.
We can back.
Okay.
In this case, a moment. Okay. In this guide, I show you the exact solution, but if we don't have the exact solution, we use the 29 by using the numerical solution, and we can compute the solution of the fraction equation. And by means of 30, we obtain, in this case, the exact solution, the numerical solution of the original model. Here is reported the exact solution, but we can use the numerical one. By two inverse transformation, we can back in order to obtain. It's important that we make the transformation only once, and after we study only the new reduced function.
And the transformation is always numerically stable, so it doesn't need to.
Because no, they are only the.
You don't need to have.
They are only the computation, the arithmetical computation.
Oh, I see.
Okay. Example, for example.
It's just the square root. I see.
Okay.
Thank you.
So maybe I didn't understand well. Why there is a so huge difference in the CPU time between L1 and trapezoidal? There's an explanation. Is related to the number transformation? Maybe
No.
Because the difference in time in CPU times was
3 order of magnitude.
Because for the L1 method has to do some computation, because we have one. Okay. we have to solve the question number 35. It depends on the form of the f itself. It's not linear function. We have to solve the Newton method for the method. So it's normal that by applying a numerical method for partial differential equation, the computation cost is higher than the trapezoidal, but not that it can be possible to use another kind of numerical methods for solving partial work. We propose these methods for their properties, but
Okay.
Faster
This is an example, just for describing the procedure, our procedure to propose the recipe. Okay.
Thank you very much. There is no. Okay, so thank you again. Speaker of this afternoon, fifth afternoon session. So we now have the coffee break, and we came back at 4:30 for 2 online talks.
adesso è lui che sta mandando.
Ok. Welcome again. The pleasure to introduce Professor Luca from the University of Formia about the same group approximation to fractional elliptic equations.
Good afternoon, everybody. First check is with the communication. You hear me fine?
Okay, we can hear you.
Okay.
We see you and we can hear.
Perfect. Now it's only up to me to say not so clever things. Okay. Well, first of all, I would like to thank the organizer for the invitation to this workshop, which so far has been extremely interesting. And on the other hand, I have to apologize for not being there in presence, but unfortunately, we are not back in full travel mode for my institution, so I will have to present this talk in remote. Okay. The work that I'm presenting today is mainly a joint work with Nicole Cusimano, a former postdoc of mine at Beckham in Bilbao, which is my former institution, and Félix del Teso, who is currently at the Universidad Complutense de Madrid. The problem we are interested in is actually the solution of the fractional elliptic Laplacian with a right-hand side f and some suitable boundary condition on the boundary of the domain. In these settings, S is a parameter between 0 and 1, omega is a bounded domain in Rn, and we are considering the spectral fractional Laplacian associated with some homogeneous boundary conditions on the frontier of omega. We consider in particular Dirichlet, Neumann, and Robin boundary conditions. For the rest of my talk, since we are considering the spectral version of the fractional Laplacian, we will always indicate the PEDX B to stress the fact that the operator is actually boundary condition dependent. So when we started studying this problem, we were actually interested in more a practical application of the fractional calculus, and it was in terms of studying the heterogeneity of the cardiac model, and for that we needed to consider a situation where we don't have just a classical Dirichlet boundary condition. So the spectral fractional Laplacian, as probably is being already discussed and will surely be discussed again by Abner later, is defined on a Lipschitz bounded domain by considering the eigenpairs of the classical Laplace operator associated with boundary conditions B. So if we consider normalized eigenfunctions, then the powers of the Laplacian of the spectral Laplacian with the boundary condition B of order S are defined as through a sum where we multiply the spectral decomposition, every term of the spectral decomposition with respect to the eigenpair by the S power of the associated eigenvalue. And this is defined for all functions that belong to L2 and they do have a convergent associated sum. We had, let's say, an indirect approach to the problem. At the beginning, we were just focusing on what is actually the action of the spectral fractional Laplacian, and from that, we then moved forward to, studying the action of the actual, how to solve actually the elliptic associated problem. So the spectral fractional Laplacian is actually equivalent in a bounded domain to a semigroup for an heat semigroup formulation. So the action of the fractional Laplacian of order S over a function U can actually be computed by solving a heat equation whose initial condition is actually U on the domain that we are interested in, and where the boundary condition are actually transferred to the heat equation. So to some extent, it's like we're dumping we dump the boundary condition into this heat equation. And once we have the solution of the heat equation, what we have to do is to compute the integral over this, let's say, auxiliary time, because we're not really having time as a variable of our problem at the moment. And we integrate between 0 and infinity the difference between the solution at time t of the heat equation and the initial condition with respect to a metric which is 1 over t to the power 1 plus s, where s is the order of fractional Laplacian. Now, what is the advantage of this formulation? The enormous advantage of this formulation is that what we have to do at this point, if we want to approximate the action of this operator, is actually splitting the problem into two. A problem where we have to solve a standard heat equation with the boundary conditions that are imposed on that boundary, and then we have to approximate a one-dimensional integral. And this is what you actually do. So what we do is to solve the latent heat equation by finite elements on the domain. And the algorithm that is written there is just a classical theta method where you can go from purely explicit or full implicit methods. And then we approximate the integral term by a suitable quadrature. So that was the first study that we did. And so the question is how to approximate this quadrature of the one-dimensional integral. So let me just give you an idea about what was the approach when we started considering this problem. So the idea is to replace the integral, which is an infinite integral of wx, w minus u, with a finite sum. Well, a finite sum. Let's say we end up having a finite sum, but a priori there could be potentially an infinite sum. So we consider a uniform grid for the integration in time, and we split the integral into three parts. So those three parts we split the integral into are the singular part, because we are integrating a function of where we get a power of t higher than 1, so we have a singularity next to the origin. So we consider a first portion, which is the singular part of this integral, a middle part where much of the things are actually happening, and then a tail. The tail, to some extent, one could, in principle, say, okay, we are dealing with a heat equation, so this thing is going to go to a steady state, so we can just discard it. And that was the first assumption approach that we had. Also, we discarded the singular part, but then we came up with something which was a little bit more accurate and under some suitable hypothesis of regularity for the domain and the Dirichlet boundary operator, and the fact that we use a quasi-uniform family of triangulation. We ended up by approximating this integral by means of Lagrange interpolant in the middle part, a non-zero approximation of the singularity, which relies on the solution of the heat equation, and then we just do an approximation for the tail, where we're just considering what is the result of that integral from a certain time forward. I'm going a little bit fast through this because this is just to tell you about how we ended up dealing with the problem that we ended up at the end. So we got a good result for this study, and we could see that we can have an approximation in the L2 norm, which under some suitable assumption between in terms of the choice of the integral step, of the time step for integration and the spatial step for the discretization of the heat equation, we end up having an error which is of the order of h to p times 2 minus s, which is considering that s is between 0 and 1. This gives us a reasonably decent approximation in terms of the convergence of this scheme. We did some tests on that, but I'm getting a little long on that one, so I'll be pretty fast. Let's say that we consider normalized eigenfunctions. So if you have a normalized eigenfunction, then the action of the spectral fractional Laplacian is just the product of the eigenvalue to the power s times the function itself. We choose 3 different cases for the Dirichlet, Neumann, and Robin cases, where the coefficient in the Robin case are suitably computed. And we can see that we had actually the correct estimation that we expect to have in terms of convergence to the exact solution. And here you can see the action of the fractional Laplacian for different values of s to the same function that we choose as a test function. Now, this first step actually allowed us, for instance, to solve a fractional porous medium type equation. When you have a time-dependent problem, then you can just do an explicit scheme in terms of the approximation of your problem. So you just throw all that is not the time derivative to the previous time step. So it's just a matter of updating the solution that you compute previously. And by paying a CFL condition, which is naturally coming out when you are dealing with the time-dependent problem in an explicit fashion, you can see that the numerical solution that we compute was actually recovering exactly the kind of behavior that we could see for the solution that was predicted by a paper by Matteo Bonforte and colleagues. But that's just what you can do in terms of the, say, the direct application of fractional Laplacian, the action of a fractional Laplacian. What can we actually do when we want to deal with the elliptic problem? Well, basically, building on that knowledge, we've been able to provide a solution also for the elliptic problem. So if your function f is suitable, and then the solution can be expressed just again as a series of powers of eigenvalues multiplied by the coefficient of the expansion of the function times the eigenvalues of the Laplacian itself, which again has an equivalent integral formulation involving the its semigroup. What does it change with respect to the previous situation? In the previous case, we had a minus s in the function of gamma and a 1 plus s in the integral. Here we got a gamma of s and we got a t to the 1 minus s. So there is a switch in the roles of those powers. Now, the equivalence of those two representations follows from the expression of the semigroup on the one end, and from the identity that we put here on the slides, which is valid for all lambda and all a, which is strictly positive. So how do we approximate then this solution? As you can expect, the idea coming from the direct application of the fractional Laplacian actually comes into play also here. So once again, we solve a heat equation with initial condition f now with finite elements. Now in this indication here, k and tau are the order of the finite element solution in space and time respectively. So if you have a second order, then tau is in time, then is 2, for instance, a Crank-Nicolson scheme, while k is just the order of the finite elements. And then we have the 1D integral. In the 1D case, we can truncate the tail after a suitable choice of t, and we can approximate the rest with a family of quadrature rules. Now, what is the difference with respect to the previous case? Before we had the singularity at the origin. Now we have the singularity at infinity because of the power of t. But the good thing is that the exponential decay in time of the solution of the heat equation allows us to select a t sufficiently big, after which not only we are sure to have convergence, but we can actually just throw away whatever is left of it. And so we can write a quadrature rule, which reminds a lot what we've seen in the other case. In particular, the quadrature rule that we define, if we consider a function such that its integral between 0 and t with respect to the metric dt over t to the 1 minus s is finite for a certain t given and a uniform partition, then we can approximate the integral of 1 over gamma s times the integral written above by a quadrature rule where the weights are defined in this following manner that I will not go through into details, but it is one thing that I would like to point out. And the fact is that this quadrature rule is actually depending on two parameters, not only on S, which is a natural parameter because we are dealing with a fractional operator of order S, but also on R. And this R will become clear in a couple of slides, but this R will depend on the regularity of the data that we are dealing with, which means that this quadrature is not a unique quadrature, as we had in the case of the direct calculation of the fractional Laplacian, but it's a quadrature for which we choose the weight according to the regularity of the right-hand side. Now, this quadrature might look a little bit crazy, but the good thing is that we can actually characterize this in a better way. And in reality, if we these weights that I put in the previous slide are nothing but the actual result that we obtained by replacing the function rho with its interpolant defined as it is defined in there. So in particular, when R is between 0 and 2 minus 2s, this interpolant is nothing but a piecewise constant Lagrange interpolant. While if we are between 2 minus 2s and 2, then in this case, we have the piecewise linear Lagrange interpolant. But when R is, sorry, no, sorry, this one, the 2, 4 minus 2s is the piecewise linear Lagrange interpolant, while here in between 2 and 2 minus 2s and 2, here we get a special definition at the origin where we combine piecewise linear and piecewise constant interpolation, and that was done to obtain optimal convergence results. Now, what is the good thing coming out of this choice is that all weights that we can get by this computation are actually non-negative, which lead to monotone quadrature rules, which are known to be very robust. On the other hand, there exists also two constants, C1 and C2, such that for all weight beta j, these bounds are actually satisfied. This is the first one. The first bullet here is an important in consideration. The second one is more useful for proving the theorem that we wrote, which is this main result that I can state here. So under some reasonable assumption on the fact that we have omega, which is a bounded domain of classic A1, assuming that F has zero mean if the B is a Neumann boundary condition, assume the KCK of omega if we are in the Robin case, assuming a CFL, which is a relation between the relation between the space discretization and the time discretization whenever the scheme has a theta which is between 0 and 1/2, if depending on the regularity of F, and we can show that there exists constant such that actually the approximation of this quadrature rule minus the actual solution, so the error in the L2 norm, depends, of course, on the norm of F in the space to which F belong, a constant which does not depend on S and does not depend on H for some values or for certain cases for R. It can depend on A, and A this is just the relation between the delta T and H, so some sort of a CFT condition, but then the power for the convergence with respect to H is the minimum between K plus 1, where K is the order of approximation of the finite elements, and A times R halves plus S. So depending on the regularity of the right-hand side, depending on the order of the fractional Laplacian, and depending on the CFL condition that we have. So from the numerical standpoint, we did some tests to check the goodness of our result. So the first test that we did was we took a one-dimensional interval, and we considered Dirichlet boundary condition, and we picked as right-hand side lambda 1 to the s times phi1 of x, where phi1 lambda 1 is the first eigenpair of the Dirichlet Laplacian. In that case, we can know that explicitly U is just P1, and then by definition, we know that all eigenfunction phi m belongs to HRB for any R larger or equal than 0. So in practice, we can decide to pick the regularity that we want here at this stage, just in the sense that depending on the regularity, we get a quadrature rule, a choice of the quadrature rule. With this choice of the quadrature rule, we're expecting an error that depends on the quadrature rule that we choose. And that's exactly what we've been able to observe here. Here you can see the predicted in dashed lines, the predicted convergence rate and the convergence rate that are exhibited by different values of fractional parameter S. Now, how does this theorem is a pretty big beast, but what is actually telling us from the practical standpoint? There is actually a dependence on the error if we omit the logarithmic term for that specific values for R, where the combination of the K, which is the finite element regularity, the order of the finite elements, tau, which is the order of the finite element scheme in time, and the A, which is the relation between it's the power to which you raise h to get delta t, then according to those combinations, you get different type of error in terms of the global approximation. So this is what is actually summarizing the situation. So you see the worst case scenario, you get an h, or you get an h to the s if you're really in a bad situation. You can get up all the way to h to the 4 in the case that your right hand side is sufficiently smooth, regular. In terms of the computational cost, that relies heavily on the number of points that we need for the quadrature, and that depends on delta t. This is what we said before. And the delta t is chosen proportionate to a suitable power of h, and this power of h has been introduced to reduce the overall computational cost, but trying to maintain the order of convergence. So is there anything that can we do to improve this situation? Well, actually, from this perspective that you can, from this table, one can say, okay, if I take a equal 2, life is good. In reality, if we take a equal to the number of quadrature nodes as a function of S and H, in order to get the second order convergence can become dramatically huge. And in reality, what is possible, we show in the paper, that it's possible to identify an optimal value for A, which is actually 2 divided by 1 plus S, where you can achieve, again, second order accuracy, which is the plot on the right of this slide, exactly like in the case with A equal 2, but with way less quadrature nodes, which entails a major computational gain. Of course, the optimized parameter gets even better once you get S getting closer to 1, because in that case, things get to be pretty much smoother. We checked also what happens with low regularity on incompatible data. So we consider a right-hand side where which is merely L2. So in that case, R, the order of regularity over F is 0. Again, the exact solution can be expressed as a sum, as a series, but the F hat of M cannot be computed exactly. So in that case, we use as a reference solution something that we computed on a very fine mesh. And the approximation in this case is done with k equal 1, tau equal 1. So first order in space, first order in time, and delta t equal h. And we get exactly the order of convergence that we were expecting to have. We did a similar test for the two-dimensional case. And for the two-dimensional case, we consider a right-hand side, which is a checkerboard. So the domain is 0, 1, but 0, 1, and the value of the function is +1 or -1 in checkerboard manner. Now, in this case, the regularity of F is 0.5 minus epsilon for all epsilon positive. And but in this case, we can actually compute a priori. One can compute explicitly the integral coefficients f at m. The only problem is that it has to be done through a series expansion. Then we did it by considering a sufficiently large number of terms, more than 100,000. So to be sure that we had a pretty good approximation of the actual solution. And here you can see that with different values of the different order of finite elements, we actually get the expected convergence rate. And also, I would like to point out that the results that we have here are in agreement with the results that were proposed by Bonito and Pashak in their paper of 2000 and 2001. Indeed, when S is smaller than 2 minus R divided by 2, so when S is smaller than 0.75, the error decay is essentially controlled by the quadrature approximation, while when S is larger than this value, so for instance in S equals 0.8 and 0.9, the bound from the finite elements is actually becoming dominant. There is also a value for which it seems to be a little bit better, but we still need a little bit more investigation on that. And the last thing, and I'm afraid that I'm going a little bit over my time, we also did a test with different choices of boundary conditions. So we see how the fractional Poisson, the solution of the fractional Poisson problem changes when you have different type of boundary conditions on your boundary. And in this case, we consider a domain which was just 0,1, S being 0.3, and an initial right-hand side, which is the one plot depicted in figure on the left, which is 1 for x more than 1 alpha and minus 1 elsewhere. Again, in this case, the regularity of f is 0.5 minus epsilon. And so we picked here k equal 1, a equal 2. And you can see that, again, we get the expected convergence rate for this approximation. And you can see on the left picture how do the solutions actually look like according to the three different type of boundary conditions. That's roughly what I wanted to tell you. And I would say that so far we use very simple interpolation, and we use so far just homogeneous grids in time. So there is space for a lot of additional study on that. And I close with just a couple of references if you're interested in those. All the technical details of what I taught about today are there, but I prefer to spare you from pages and pages of integrals. Thank you.
Thank you very much. Thank you very much for your interesting talk. And are there some questions? Maybe just one, because we are a little bit late. Not from the chat, no? I have just a curiosity, just a few seconds. Apart from the parameter R, which depends on F, there is a way to automatically detect how to choose the other parameters of the method.
So you are mentioning
A and S, all the other guys. A.
Well,
R depends on.
R is given. R you have nothing to do with that. So I don't understand why, but for some reason it's.
Okay, no problem.
I cannot make it bigger anymore, but I hope you still see the slide. So R is what it is. K and tau are your choice of finite element. So of course, the higher the order of approximation, the better the situation. The important thing is that you have to take into account that you need to pay us as a theta, which is between, let's say, where is that? It's here, where your theta is between 0 and 1/2. Okay. In that case, you have to pay a CFL. But then the choice of A is somehow it was somehow given here in this table. Actually, this is the A opt that appears to be the best one. So it's 2 divided 1 plus S. So if we take delta T, which is H to the 2 divided 1 plus S, then you get good properties in terms of computational cost reduction.
Okay. Okay. Thank you
But
very
that
much
was,
again.
and I stress it, that was for a very simple and basic quadrature rule that we are using. So we're just using a uniform grading time. And a priori, one can think of doing something better in that sense.
Okay. So thank you very much again for.
Thank you.
And now we have last keynote speaker of the day, Professor Abner Salgado. Hello, and from the University of Tennessee. He will talk about numerical methods for spectral fractional diffusion. Okay.
First of all, technical question. Can everybody hear me? Can you hear me? Hello.
Yes,
I
sir.
can.
Thank you.
Okay, thank you.
Okay, sorry.
Okay, well, thank you very much, everybody, for being here. Thank you to the organizers for the invitation. So, what I want to talk about today is maybe something a little dangerous, because I want to give an overview of several methods to deal with spectral fractional diffusion. And of course, whenever you do an overview, you're bound to miss something. So for instance, I will not talk about what Luca just presented. I was actually not aware of those results, the later ones, but you'll see that there's some similarities or common things that will pop up. So here's my quick outline. So I will start by trying to motivate what we're trying to do. So fractional powers of an operator, maybe I'll go a little quick because Luca already mentioned them. Then I will give maybe 3-4 methods, depending on how much time I get, on how to deal with them. And yeah, we'll go into some of the details for each one of them. And please feel free to interrupt me at any time. I'll try to see if I can keep an eye on the chat. But okay, so let me start by going back to linear algebra. And just let's remember that if we have a matrix that is symmetric, then it is orthogonally diagonalizable. What does this mean? It means that there's an orthogonal matrix and a diagonal one, by which we can represent this matrix, our original given one, in this form. Q is orthogonal, so its transpose equal to its inverse, and lambda is this just diagonal, just these guys. The usefulness of this is that in this case, the action of my matrix on any vector can be described by 3 simple operations. The multiplication by Q is nothing but an orthogonal change of basis. Right? So first we multiply by Q, we change of basis, then we multiply by lambda, which is a diagonal matrix. That is just at a scaling in each coordinate direction in this new basis. And then multiplying by Q transpose, which is the inverse, is just coming back to the original basis. On top of that, if we know that the matrix is not only symmetric, but also positive definite, that means this, we know that all the eigenvalues are going to be positive. We all know this very well. We all know also that this has some applications, not just that simple decomposition of the action of a matrix, but we can, for instance, define any function of a matrix in this form. Just say compute a sufficiently nice function of a matrix just by hitting the eigenvalues, the diagonal elements of that matrix. We can represent the solution of an ODE in terms of the exponential of a matrix. We can analyze the theory of implicit iterative schemes. So some classical two-layer implicit iterative scheme to solve a linear system of equations can be written in this form, where this B is usually known as the iterator or preconditioner. And to analyze these schemes, what one usually does is do a change of variables in which we multiply essentially by the square root of this matrix B and introduce a new variable. And then you reduce it to an explicit scheme for which essentially the theory of Richardson iterations goes. And of course, I'm just giving a quick overview of possible applications here. There's many possible. Of course, this was linear algebra, finite dimensions, but it turns out that we can do something somewhat similar in the infinite dimensional case. For instance, for differential operators. And the operator that's I'm going to be mostly concerned with is the fundamental operator that expresses diffusion, namely the Laplacian. We know that if we supplement it with, say, for instance, homogeneous boundary conditions, just by integrating by parts, these operators becomes positive. We can show, and this is just Sobolev embedding results, that the solution of the Laplacian with homogeneous boundary conditions lies in what H10, which is compactly embedded in L2, so this is a compact operator. Then we have spectral theory that tells you that there's a countable collection of eigenpairs for these operators, and that means that in terms of these eigenfunctions of the Laplacian, we can represent any function L2 in this kind of generalized Fourier series representation. With the help of that, we can say now that if my function is sufficiently nice, I can represent the action of the Laplacian in terms of just first compute the Fourier coefficients, multiply each Fourier coefficient by lambda, the corresponding eigenvalue, and do Fourier inversion if you want, which is this sum. So once again, this is the exact analog of what we were doing in linear algebra, because first we compute these coefficients, that's a change of basis into the basis of these eigenfunctions. We multiply by the eigenvalue, that's our diagonal scaling, and then the sum is coming back to the original basis. With the help of this, we can now define functions of the Laplacian. So for instance, if I choose a number S, which from now until the end of my talk is going to be between 0 and 1, at least for a sufficiently nice function, I can define the fractional Laplacian, just as we did for matrices, just by applying the function, the power S, to the eigenvalues. Of course, you can define whatever you want, but you should be careful into why are you defining this? Does this make sense? What is the domain of this operator that you came up with? Or what is its range, and so on. And so let's see, why is this something that might be useful? Well, first of all, we know that the heat equation, let's say with homogeneous right-hand side but in initial condition, it's expressing diffusion. So the solution is going to smoothen and smear the initial condition. And in the very early days, this was proposed as a model for image denoising, right? Think of a big a noisy image. You run the heat equation for a little bit with it, and that is going to smoothen out the solution. That means that you're going to remove artifacts, oscillations, for instance. However, it turns out that the effect of the Laplacian there is too strong. There's too much diffusion. So you can weaken it by not applying the Laplacian, but a fractional power of it. So you get some sort of a fractional heat equation. That is something that also was used. Some sort of a fractional heat equation also appears in certain special cases of random walks. There is a whole family of models of phase transition, like phase field model, known as Allen-Kahn or Kahn-Hilliard equations, which in general look like so. So Allen-Kahn is where there's no term here, and there's a usual Laplacian here. Kahn-Hilliard is where these two alpha and beta are powers 1. And recently there has been some developments, in particular by Mark Ainsworth and his students in Brown, in trying to understand what is the effect of doing a fractional Canhillier equations, so equations of this form where these powers are between 0 and 1. And he has some interesting results, some interesting capturing of things that were not possible before. I shamelessly stole these pictures from a paper by Soren Bartels and his collaborator, in which you see the effect of essentially using this fractional heat equation to regularize an image. So on top, from left to right, we see the original image. These are like usual standard images for showing the effects of this image, the blurring algorithms. And you see that there is indeed, this is your blurry image. And here is what you get after using some sort of fractional heat equation to deal with this. So there is some applications to trying to deal with this fractional Laplacian operator. Luca mentioned in his talk just another one, which was trying to capture the heterogeneities of human tissue. I think his motivation was the heart. He can correct me if I'm wrong. But one of the interesting things here is that also this was not something that was unique to the Laplacian. We can do the same for any other symmetric second-order elliptic operator. We can again supplement it with suitable boundary conditions, and we can also define fractional powers of this operator. So that gives you a lot of, if you will, modeling flexibility, because now you have not only the power to play with, but also the coefficients A and C. Of course, let's try to keep life simple, and for the talk, let's just focus on the fractional Laplacian. So C0 is the identity. Now, so the goal of this talk is to try to see, well, let's say that I have a function f, a right-hand side, and I try to find a solution u to this problem. Fractional Laplacian, power s, which is between 0 and 1, applied to u equals to f. In the sense that we described above, meaning in the sense of spectral theory. From the definition of spectral theory, you can see that there's an immediate thing that you want to try. Find the eigenvalues and eigenfunctions of the Laplacian and do this sort of a generalized Fourier decomposition. The catch here is that the domain is general. If you had a very simple domain like a square, you can do separation of variables or something like that to find the eigenfunctions. But if it's a general domain, then that's not so easy. And that's the essence of the difficulty here. So what can we do? Well, first, we need to take care of some technical issues. Namely, we need to understand what is the domain, range, and regularity of solution that we can expect. Because there's no hope of doing rigorous numerics if you do not understand the regularity of the solution of the object that you're trying to approximate. And so this is mostly notation that I'm going to use. My fractional Laplacian is going to be a function that acts from this fancy HS to its dual, where this is just functions that, depending on the eigenfunction of the Laplacian, are square summable, if you want, with some power of the eigenvalues. And it turns out that there is some equivalence between these spaces and classical fractional Sobolev spaces. So HS, the classical fractional Sobolev space, if you're between 0 and 1/2, HS with 0 boundary values, if you're strictly larger than half, and as always, the case 1/2 is special, and in that case, you get the Lyons-Marchesne space. And so, and of course, the fact that we're dealing with fractional Sobolev spaces gives you the idea that you're dealing with fractional derivatives, fractional regularity functions. And like I said, if we want to understand how to approximate properly the problem, we need to understand the regularity of the solution. And from the definition, if you work in these fancy H spaces, just by the definition of the fractional Laplacian, you have an immediate shift. If your data is in HR, then your solution is in HR plus 2s. If you try to translate this into usual Sobolev spaces, then at least in the interior of the domain, you're going to have the same regularity shift. However, and this is a series of results by, for instance, Caffarelli and Stinga, that they show that close to the boundary, bad things are going to happen. And that has nothing to do with the domain, that has nothing to do with the regularity of the data, that has some intrinsic difficulty in the problem. And namely, they show that if S is different than 1/2, then there is the solution has this kind of asymptotic expansion as you approach the boundary. The solution is something smooth, call it B, times the distance to the boundary to this power. Of course, S is between 0 and 1, so this power is minimum of 1 and something smaller than 1, so it's distance to the boundary to something smaller than 1. So there's, or 1 if S is larger than half. So this distance to the boundary gives you some sort of algebraic boundary singularity that you need to take care of if you want to properly approximate the solution to this problem. Of course, this case S1/2 is always exceptional, so there's a logarithm that appears there. I need to, before I keep going, and before we talk about numerics, give a warning that in bounded domains, there are at least 3 common definitions of the fractional Laplacian, and they do not coincide. If you're on the whole space, they are all the same, but if you're in a bounded domain, they are different. So we have the spectral one I talked about. We have also the so-called integral fractional Laplacian, in which you compute this integral, where the tilde denotes zero extension of the function to the whole space. Notice that here the integral is over the whole space, Rd. There's another one that is called the restricted fractional Laplacian, in which the integral is only over omega. These 3 definitions do not coincide. They have very different properties. The solution of problems to these have very different properties. And so one needs to take care, or one needs to be careful into specifying which fractional Laplacian you're talking about. And so I will focus on the spectral fractional Laplacian. Let's start talking about discretization. So as I mentioned, there's, from the definition, a very obvious thing to do. Namely, since the definition of the fractional Laplacian comes from this eigenvalue expansion, then the obvious thing to do is, well, I'm going to do a Fourier expansion of my right-hand side. Each one of the modes, the FKs, you multiply by the suitable power of lambda, and then go back, right, by summing these UKs times the eigenfunctions. Of course, this may not be the very smartest thing to do, although it is the obvious one, because there's many questions here, right? I mean, we need to compute a sufficiently large of eigenpairs. So how do we choose this n? What does sufficiently large mean is not clear. Eigenvalue problems, even in the finite dimensional setting, is very well known that those are difficult. And even if we insist on going this way, it's not clear what to do with respect to error analysis, so how good of an approach this is. So let me talk a little bit about the error analysis, because that's something that's can give insight into some other approaches. And there's this 93 paper by Matsuki and Ushijima that is not very well, doesn't have the attention that it deserves, I think, that do the error analysis of this approach in a very general setting. So they looked at the Hilbert space, some positive definite self-adjoint unbounded closed operator in that space. I'll translate this in a little bit. They assume that they have some family of closed subspaces, and on each one of them some positive and unbounded operator. And you assume that this operator AH has some sort of inverse estimate. So since it is bounded, there's a bound, but that bound may depend on H, the parameter of these subspaces. There is some sort of approximation property regarding the inverses of AH with respect to the inverse of A in this sense. And in that case, they were able to show that if you compute on the subspace using this discrete operator, if you will, you'll get an error of power this epsilon, that is the parameter that appears here, to the power s. Let's translate this into the fractional Laplacian case. So our space is going to be L2, xh, let's say you use finite elements, piecewise linear, for instance. A, of course, is going to be the Laplacian, and AH is going to be some discretization, say solving the Laplace problem in a finite element context. We need some sort of inverse estimate. That means that, well, since we're dealing with finite elements, they're piecewise polynomials, they have attached to it a mesh. So things cannot move more than on a mesh scale. And that's why the Laplacian has, well, two derivatives. So it scales like 1 over h squared. So your epsilon here is going to be h squared. Using, for instance, full regularity and an open niche duality trick, you can show that the approximation of the Laplace problem using finite elements is of order h squared. And so the previous, this previous theory tells you that, well, if we were going to go this direct discretization approach, then the error that you commit in L2 is of order h to the 2s, which I think is some of the results that Luke already was getting. I think in the case that R was 0 and A was 2 or something like that. But of course, we still need to compute this, the inverse of the Laplacian to the power s. So, of course, you can do all the eigenvalue decomposition, but that's still complicated. So maybe there's better approaches. And one of them is known as the best uniform rational approximation. So, like I said, evaluating the eigenvalues of the discrete Laplacian is very time consuming, although there are methods for that. So instead of this, there's an approach proposed by Rachel Lazaroff and his collaborators, and they have been working on it for quite a while, in which, let's say that now we're at the linear algebra level. So these are matrices that come from these discrete problems. And so you need to solve this problem. A to the s applied to u equal f, where A is some sort of rescaled version of this discrete fractional Laplacian. What you're going to do is try to come up with some analytic function that approximates this function, t to the power 1 minus s. It has a uniform approximation of 2 order epsilon. Then if you, instead of computing a to the power 1 minus s, you apply this function r to the matrix A, you're going to get some approximation power in terms of this epsilon, the approximation in terms of functions. And so if you were to apply this matrix R, this function R to the matrix A, and use that to solve your problem, let's say in this form, then you're going to get an error of power of order epsilon, which if you combine with the previous results, you get that the full error is of power 2s plus this epsilon. Of course, here's everything very high level because I said, okay, apply a function to a matrix. We still need to find out what that suitable function is. And that's the point of best uniform rational approximation, because here you have a uniform approximation, and so your function R is going to be a rational function. So, and a rational approximation is a topic that is very well known, very well developed. So the point is you're going to choose this RS to be the best uniform rational approximation. M and K are the degrees of numerator denominator to this function. How to find this is very well known. How to find the coefficient of this rational approximation is well known. And now what you're going to do is apply a partial fraction decomposition to that rational function. You get an expression like this, where, like I said, these coefficients, little b's, little c's, and big capital B and C, and everything else, there's ways to compute them. And so all that you need to do now is hit your data f with this rational function, which essentially means, okay, multiply your f by powers of the original matrix, or solve either, well, the original matrix, A inverse, so solve a linear problem, or solve shifts of the original matrix applied to f. So, of course, the question is how to choose the degrees, and that's, like I said, that is very classical and rational approximation. And if you do an optimal choice, then you get an error that decays exponentially in the polynomial degree. So the effect of this part of the approximation, of choosing the rational approximation, can be minimized. I mean, exponential compared to the h to the 2s that we had here is very small. So as an outlook, if we want to solve this problem with a best uniform rational approximation, all that we need to do is solve a few problems of the type, say, discrete convection reaction, shifts of the Laplacian, and you just gather them together. These problems do not talk to each other. They don't see each other. Once you know the C and the G, you can send that to your processor. Then you can send a different one to your friend, to your neighbor. You gather them together, and that makes this embarrassingly parallelizable. And you get an error estimate of order, well, to h to the 2s. There's questions here to be addressed, and for instance, how to do an error analysis in some other norms, how to deal with some other types of problems, for instance, time-dependent ones, nonlinear ones. And there's an issue that even though the topic of rational approximation is very well studied, because of that is also very well known, that's this is very sensitive to numerical bound, in the sense that there's ways to find these coefficients, but you need to be very careful. I think I read somewhere that you need to use something even quad precision sometimes to find these coefficients, otherwise you get into stability issues. But this is one way, and I want to reiterate that to solve with this approach, all that you need to do is solve a series of convection reaction problems, pretty much as in Lucas' approach. Let's talk about another approach that is known as the Balakrishnan formula. And I don't know where I started, so stop me at any point whenever you think that I'm out of time. So the Balakrishnan formula is the following.
Excuse me, Abner.
Yes.
Abner.
Yes.
Excuse me, since sometimes we have some troubles in hearing, maybe there's a problem on the connection. I would like to suggest you to switch off your camera, so your bandwidth is all dedicated to your voice slide. Sorry for interrupt you.
No. Yeah, please, thank you for telling me. I didn't know. But yeah, is it better now? Can you hear me now?
Yeah.
Okay.
I always heard you fine, but I'm not in the room, so.
Oh, okay. Yeah, okay. Yes, please stop me, interrupt me if something is not clear or if there's connection issues.
It's okay.
Okay, so the second approach that I want to talk about is the so-called Balakrishnan formula, which is based on some integral. If you deal with special functions at some point, you will encounter this formula that for any lambda positive, or for any theta between 0 and 1, lambda to the power theta minus 1 can be expressed like as this integral. Okay, so now if you apply a little bit of functional calculus and say if you have a self-adjoint positive and closed operator on a Hilbert space, essentially by replacing lambda by that operator, this identity stays valid. And this means that if you want to compute the operator A to power theta, well, you can do times A to the theta minus 1. And for this, you can apply this formula. Okay, so that's what we do here. And now this gives you a way to compute or to a formula for the inverse of the fractional Laplacian. Namely, well, the inverse of the fractional Laplacian is the inverse of the Laplacian times the Laplacian to power 1 minus s. And for that, you apply this formula with theta being equal to 1 minus s. It's complicated, I know, but the point is that fractional Laplacian to power minus s can be represented by this, where the point is that here we only see shifts again of the Laplacian, t times the inverse, the Laplacian and inverted. So the approach now is going to be very similar to what Luca was doing. Namely, we're going to use this formula or this representation to construct a numerical scheme, and we're going to do it in, well, in 3 stages as I have pictured here. First, we're going to replace this interval by a quadrature. I'll try to explain a little bit what quadrature to use. Now here, what we have is a solution, again, of diffusion reaction problems. So we're going to use finite element methods on the same mesh. This is kind of important for technical reasons. On the same mesh to approximate the solution to each one of these problems. And then I'm going to gather all contributions. So to the quadrature rule that turns out to be the correct one or a good one to do here is something known as a sinc quadrature, which consists on 2 things. First, we're going to do some change of variables, and then we're just going to do a trapezoid rule. So yeah, that's essentially it. And the general theory of sinc quadrature shows you that you get exponential convergence in terms of the number of nodes that you do in this way. Then each one of the problems at the quadratic nodes that you need to solve, you approximate with finite elements. This makes the problem, again, embarrassingly parallelizable because once you know your quadrature nodes, these problems are set up, they don't talk to each other, and so you solve them independently and you gather them together. And so you obtain this, if you want, representation of the approximate solution to your problem. Their analysis, and this is based on a paper by Bonito and Pasiak and some further developments that they did, is, well, it's complicated, but what I want to point out is that in the best case scenario, the error that you get is of order h to the 2s, which again is an order that Luca had already shown in the case that we had an optimal regularity on the solution and optimal regularity on the right-hand side. This, of course, is not always generic. He also talked about this. But to recap, once again, to solve the fractional Laplacian problem with the Krishnan formula, all that you need to do is solve a few problems of this type and gather them together. That makes this approach embarrassingly parallelizable, and it gives you an error estimate that in the best case scenario is optimal. Again, this is I think one of the issues with this approach and the previous one is that we are applying a formula for the inverse of the operator. So it's not so clear how to translate all these to other types of problems, for instance, time-dependent or nonlinear ones. The error estimate is done assuming that you have a lot of regularity and compatibility, which is expressed in the fact that we have this fancy H here on the data, and it's not so clear what to do in the case that that does not happen. Because, and I skipped this, but I can rewind a little bit, the analysis of this approach is done assuming that your mesh is quasi-uniform. At some point, you need to apply inverse inequalities, and if your mesh is not quasi-uniform, things don't go well. And as I mentioned before, there is an algebraic boundary singularity that will always appear no matter what you do. So it's not so clear how to capture the boundary singularities of the solution in this approach. So with that, let me come to the last method that I want to talk about, and is known or is based on the so-called Caffarelli-Silvestri extension and some tensorization approaches that we worked on with several collaborators over the years. So to explain it, I want to begin by mentioning how to define the square root of the Laplacian on the whole space. And that is done by the so-called Dirichlet to Neumann operator. So let's say that you have a function defined on Rn. Rn is this line over here. And let's say that we extend it harmonically to the upper half space, to Rn plus 1. This should be a plus 1, sorry. So you're solving this problem. Minus Laplacian of big U is equal to 0, meaning capital U is harmonic. And you take as Dirichlet data at the bottom of this half space, your original given function, little one. You solve this problem, and now you compute the normal derivative at the bottom of the half space. So it's some sort of a Neumann boundary condition. That is the Dirichlet to Neumann map. So you take your function in Rn, extend it in one more dimension, and then you come back with a normal derivative. It turns out that this operator has several good properties. Namely, if you apply it twice, you get the Laplacian of the function, and that's just because the extension is harmonic. This operator is positive, once again, just by using that this extension is harmonic and some by parts. And so if you have a positive operator whose square is the Laplacian, it's not inconceivable to say, well, we're going to define the square root of the Laplacian to be that Dirichlet to Neumann operator. This is something that had been known, I think, in potential theory for many, many years. And in 2007, Caffarelli and Silvestri came up with a generalization of this approach to any power s. As with all great ideas, this has appeared in many other incarnations, in flavors and so on, in many other papers. In fact, it was known in the probability literature since the late 60s. And the idea is the following. Let's say that you want to solve in this domain omega, this problem, fractional Laplacian of s applied to equal f, same problem that we had before. You're going to take this domain and extend it in one more dimension. So here, let's say omega lives in x1 and x2. You extend it in one more dimension y into a semi-infinite cylinder, which from now on forever I will call fancy C. In this cylinder, now you're going to solve this problem. Divergence of y to the alpha applied to gradient of u equals 0. Y is the extra dimension that we introduced. And alpha is a parameter that depends on s, the power that you want to compute. So alpha is 1 minus 2s. You solve that problem where you take as data here on the bottom of this cylinder, well, a Neumann data. So conormal derivative, and conormal with respect to this operator, derivative of the solution is equal to, well, some number for normalization purposes times f. You solve this problem, which is now a local problem, albeit in one more dimension. And then you go back and compute the trace of the solution to that problem at y equals 0. And it turns out that what you get is the solution to this problem, the problem that we were wanted to deal with first. So once again, fractional powers of this Laplacian can be realized as generalization of the Dirichlet to Neumann operator. With, well, by just computing the solution to this Neumann problem and then taking its trace. The good approach here is that, like I mentioned, this is a cylinder, right? So you can apply separation of variables. And by applying separation of variables, if you look only at the y components of this equation, you get this ODE, which turns out to be a Bessel equation whose solutions are going to be these modified Bessel functions of the second kind times some factors. Here, lambda is playing the role of the eigenvalues of the Laplacian once you do separation of variables. The good thing is that once you know the solution to these Bessel functions, you go to your favorite book in special functions, and there's everything that you want to know about the solution of these functions. Say, for instance, we know that as y or z goes to 0, these functions are going to behave this way. So we just need to normalize them to get that at 0 you get lambda to the minus s, which is what we want. Solve the fractional Laplacian power s. This also helps you in having a solution representation to this harmonic extension. Namely, if you had a function f that is your data, we know that the solution has this representation. And so applying separation of variables, you know then that the solution to the extended problem has this representation, where now this size are going to be solutions to this Bessel equation. So you know they're going to be these modified Bessel functions. You can use this to derive a very refined regularity theory that's I don't have time to detail, but the point is that you have a lot of information of the solution to this problem, and so you can say a lot about the regularity of the solution to this problem. And so our approach then is going to be, well, we're going to approximate the weak solution to this problem, because now this is a local problem in an infinite domain, but it's a PDE. It's something that we know how to deal with. And because we have this weight, we need to do a little bit of acrobatics in dealing with that weight, because that weight is either degenerate or singular. But this can be handled by some theory of so-called Muckenhaupt weights. I don't want to get into details there, but the point is that everything works. This alpha harmonic extension is under control, and so we can discretize. So this problem, this is a cylinder, the original domain times 0 infinity. Alpha is 1 minus 2s. ds is a number that we know. So this is the problem that now we need to deal with. The advantages that I see in this approach are, well, now we're dealing with a local problem, just so you can implement this in the easiest incarnation in just your favorite finite element package. It is very flexible, and maybe I'll have time to say a little bit more about why. Of course, nothing is free in this life, because we have to deal now with an extra dimension. But yeah, we have to deal with one extra dimension, but we have ways of mitigating this, and I will mention some of this in a little bit. There's also the issue of this degenerate or singular weight, but that is also under control with the fact that this weight is in some very particular class. So let me go to discretization. And so the latest version of this approach is taking advantage of the fact that we are working on a cylinder, and so we're going to do what we decided to call tensor product finite element methods. And so the first step is, well, we're dealing with finite elements. Those are suited for bounded domains, but we have an infinite cylinder. So what we're going to do is truncate the cylinder. Just say, well, it turns out that you can say that the solution to the original problem decays exponentially as you move in the extended direction. And so we're just going to chop at some height, capital Y, and live with it. That it turns out that that's not a bad idea, because the error that you commit in doing that is exponentially small in terms of this chopping parameter, capital Y. That is the first step. Now we're dealing with an elliptic problem on a bounded domain. You can do whatever you want there. What we want to do is take advantage of the geometry of that domain, namely that it is a cylinder. So it's a Cartesian product. And so we're going to first discretize only in the extended direction. So here we have a mesh, any mesh that you want. And so we're going to first do a semi-discretization. So we discretize in the extended direction, but we do not discretize in the original directions on the domain omega. And we compute this semi-discrete solution. But we don't compute it, we define it, this capital UM. And that one turns out to be, again, exponentially close in terms of the degrees of freedom in this semi-discretization to the original solution of the problem. Now, to achieve this, we need to capture the singularity that comes from going to y equal to 0 in these modified Bessel functions. So it turns out that then this mesh in the vertical direction needs to be geometric or suitably refined towards y equals 0. But if you do that, and if this is in one dimension, so constructing geometric or graded meshes is not a big deal, then you can get an exponential order of approximation. Now, the next step then is to approximate in the original directions, but before doing that, we're going to diagonalize our problem. So we're going to, in one dimension, solve this collection of eigenvalue problems. And this is in one dimension, the y dimension. These are going to be, if you want, it's going to be the same step as choosing the quadrature coefficients in your quadrature formula. This is done once and forever. This is the same as computing the coefficients in your rational approximation. This is done once and forever. And that gives you a representation for your semi-discrete solution in terms of the generalized eigenpairs of this problem. But this is a discrete problem, and again, it's in one dimension, so it's much easier than going and doing an eigenvalue expansion of the original Laplacian. And now you can discretize independently each one of these capital U's by solving, as before, as in all the approaches that we had before, solving a convection diffusion problem. These capital A's, this little a mu, are these bilinear forms. The mu is the eigenvalue. And so again, it's a diffusion reaction problem. Sorry, I'm saying something different. Okay, so once again, this is a very easy to parallelize process because you compute these guys, say, if you will, offline, that gives you the bilinear forms A and the numbers mu. You solve each one of these problems independently, and then you just gather the contributions together. So it turns out that now you can do essentially whatever you want in the domain omega. So for instance, we can do P1 finite elements. We can even handle reentrant corners in 2 dimensions. So you can suitably grade the mesh in the omega directions to capture the singularities that come not only from the data, but also from the solution of the fractional Laplacian itself, and get an error estimate of this form. So for the h, however, the dimension is n, the number of degrees of freedom to power 3/2, that's suboptimal. Well, that is because you're using too much information on the domain omega. You can do some other things. For instance, you can do sparse grids in the sense that you use some sort of multi-level decomposition of the domain omega in terms of the levels in the vertical directions. If you do that, you can get an error estimate that is optimal with respect to approximation and with respect to order. You can do, for instance, HP finite elements in the extended direction and P1 finite elements in omega. And once again, get error estimates that are optimal with respect to everything. Or if you want, you can do HP in omega and in the extended direction, and even get exponential rates of convergence with respect to the number of degrees of freedom. I just a small numerical experiment, because I know I went very fast in all these results. Let's say I have an L-shaped domain in 2 dimensions. F is equal to 1, which is smooth but not compatible. And you see that, for instance, if the blue line is doing P1 finite elements, so the rate of convergence is optimal in the sense of approximation, but it's not optimal in the sense of degrees of freedom. But either sparse or HP finite elements in both directions gives you an optimal error error estimate. So n to the minus half in this case. I think I should conclude, and I apologize for the technical difficulties. But so with this last PDA approach using the Caffarelli-Silvestri extension, we were able to convert a non-local problem into a local one, albeit in one more dimension. And because we were not dealing with a formula for this inverse of the operator itself, but for a new representation of the problem, if you will, this is very flexible. For instance, you can very easily accommodate this extension to handle parabolic problems, nonlinear problems, obstacle type problems. I gave you, maybe very quickly, but I talked about complete and quasi-optimal a priori error analysis over anisotropic meshes. That, for instance, if you use P1 finite elements in omega and P1 finite elements in the extended direction, gives you suboptimal complexity and linear rate. We can use sparse tensor representations that gives you a quasi-optimal complexity and quasi-optimal rates in terms of approximation. You can do HP and get exponential rates of convergence. And we have many other extensions. For instance, we have multivariate methods to solve the ensuing problems. We have a posterior estimation to targets to adaptive finite elements. However, I mentioned we have a posterior error estimators, so you can do adaptivity in practice, but there's no theory to guarantee that this is a good thing. So convergence optimality of adaptive methods is still open. All the computations that I showed are when the domain omega is in 2 dimensions. An efficient implementation of this in 3D, in the sense that the extended direction is not actually meshed, but it's just there as an aid, is open. And our HP implementation and analysis is restricted to 2D. So in 3 dimensions, this is completely open. And with this, I will finish. Thank you very much.
Thanks to Professor Salgado for his interesting talk. Are there any questions from the chat or from the audience here?
Hi, I have a question, if that's okay.
Lechel, yes?
Hi, Abner. Hi, Abner, it's Lechel.
Yeah.
Just a question on your comparison of the Balakrishnan and extended, because you mentioned something about assuming the compatibility of F, needing that for the Balakrishnan, but not for the extended.
You mean here?
Yes, it's just because we have a recent preprints on HP in 2D polygonal domains, both for the Balakrishnan and the extended, and
Sorry,
it all goes to the. Sorry.
Yes, sorry.
Sorry, can you repeat? We cannot hear. Non è che gli danno.
Should I repeat the question?
I heard you very well. I don't know if the people in person could hear.
Provi a parlare, è molto complicato.
So what do we do?
I don't know if...
Hello?
Ah, no, non credo, perché se non sentiamo noi non sente nessun altro.
Okay, I don't know what's going on, Lechel. So you can hear me, right?
Yes, I can hear you well, yes.
All right.
I can hear you as well. I'm afraid the problem is only for the room.
Ah, okay.
Okay. So you're saying that you have a new preprint in which you can handle with HP incompatible data even for the Balakrishnan formula?
Yes, it all goes back to the reaction diffusion equations, and then we use results of Marcus's. So this is with Melling and Schwab.
Yeah, I see.
We use the results of Marcus Melling from his habilitation on reaction diffusion equations. So this is analytic data, but not necessarily compatible.
Yeah. Well, I mean, I warned everybody at the very beginning, right? I'm more than likely I'm forgetting something, but I didn't know about that preprint. Thank you. Yeah,
it's an archive, but yeah.
Okay. No, but the issue here, if you remember the original paper by Bonito and Pasiak, they need to have quasi-uniform meshes.
But I mean, we did the full analysis. We didn't need that. I don't know where that's coming from.
Yeah, I mean, from what I remember, I mean, I read this paper, what, 5-6 years ago.
Because I mean, the tiles, well, the contour integral error can be done separately, and then And then you have a series of reaction diffusion problems. So I don't.
Yeah, so I think, let me see if I remember.
I don't see fundamentally how it's different, but maybe I'm missing, probably missing something.
I think at some point they need some sort of stability of L2 projection in H1 or something like that.
Okay. Okay, I mean, yeah, we need we are using somewhat special meshes where Marcus did all the details back in his habilitation and have all these estimates. But yeah, okay, depends how what tools you use.
Yeah, I mean,
depends what tools you use. Yes.
Yeah, so I mean, like I said, I'm more than likely forgetting almost everybody here. And thanks for letting me know about that paper. I didn't know about it. I'll check it out.
Sure. Anyway, but thanks for the nice talk. It's nice to see all these things in one talk. Yeah.
Yeah. Thank you.
Thank you very much again to Professor Salgado. And I wish to give you appointment to tomorrow at 9:30 for the second day of the workshop. So goodbye and see you tomorrow.
Thank you.
Thank you, and I'm sorry for the technical issues.
Okay, thank you. No, maybe the problem was on our side. We don't know exactly. So, however, we were able to attend, to follow your talk. Thank you again, Abner. Thank you. Bye. You're very nice.
Thank you very much.